Hi, I'm Swarupa Sail, course instructor for fluid mechanics. In this presentation, we will learn about stream function. Stream function is the scalar function of space xy and time t, such that its partial derivative with respect to any direction gives the velocity component at right angles to that direction, and it is denoted by psi. It allows simplification of basic two-dimensional flow using single variable, that is psi, which is function of space xy and time t. It is defined for two-dimensional flow and for steady flow. So as per definition, its partial derivative with respect to any direction, that is dou psi by dou y, will give us the velocity component which will be at right angles to this direction. So u is the velocity component along x direction. Hence, we can see from this equation that partial derivative of psi with respect to direction y will give us the velocity component along x direction. Similarly, partial derivative of psi with respect to direction x will give us the velocity component, that is v, which is along y direction. This can be more clear when we look at the sketch over here. Let the directions be indicated along x, which is positive direction, y is positive on top, and y is negative at the bottom, and this is what is negative x direction. Let u be the velocity component along positive x direction, v is the velocity component along positive y direction, and u is velocity component along negative x direction, and similarly v is the velocity component along negative y direction. Now here from this equation, we can see that partial derivative of psi with respect to direction x, so this is what is the direction x, will give us the velocity component which will be at right angles to the direction x. So the partial derivative of psi with respect to x will give us the velocity component v, which is at right angles to x direction. Similarly, the partial derivative of psi with respect to direction y, that is positive y direction, will give us the velocity component which is at right angles to y. So the velocity component which we get is minus u. Continuity equation for two-dimensional flow, as we know, is dou u by dou x plus dou v by dou y is equal to 0. So when we substitute equation 1 and 2 from the previous slide in this continuity equation, we will get Laplace equation. So dou by dou x of u, which is minus dou psi by dou y, plus dou by dou y of v, which is dou psi by dou x, will be equal to 0. So final equation will be minus dou square psi by dou x dou y plus dou square psi by dou x dou y will be equal to 0. So there will be possible fluid flow if this equation is satisfied. To find whether the flow is a rotational or irrotational flow, we need to find rotational component with respect to stream function. So omega z will be equal to half of dou v by dou x minus dou u by dou y, which will be equal to half of dou by dou x of v is dou psi by dou x minus dou by dou y of u is minus dou psi by dou y. So final equation will be half of dou square psi by dou x square plus dou square psi by dou y square. Omega z will be equal to 0 for irrotational flow. And equation dou square psi by dou x square plus dou square psi by dou y square equal to 0 is known to be the Laplace equation. Now we will look at the properties of stream function. If stream function exists, it is a possible case of fluid flow which may be rotational or irrotational. And if stream function satisfies the Laplace equation, it is a possible case of an irrotational flow. And we have seen the Laplace equation, which is dou square psi by dou x square plus dou square psi by dou y square is equal to 0. Thank you.